All right, so we talked about circuits in parallel or in series. Now I'm going to talk about circuits that are in parallel. The difference is that in a parallel circuit, when current is being created, when you hook the voltage up to your circuit, and current is being created, the current at some point bifurcates, splits. It goes in different pathways. So a current that's leaving this battery or this voltage hits this part of the circuit, and it has a choice to make. It can either go through the top, or through the bottom, or through both. Well, the current is going to look at it as multiple pathways. So what it's going to do is it's going to split. It's going to create a current that goes in this direction and a current that goes in this direction. Okay? And we'll call that I1. We'll call that I2. Okay? So it makes this initial total current that comes out of that battery, hits that point, bifurcates, and then goes one way here, and some of it goes down here. So I get some current down here, some current up here, and obviously, hopefully, it's obviously, the higher resistor over here is going to experience less current. Remember, resistance is this impedance to let charge flow. So higher resistance means that there's going to be less charge flowing through that part of the circuit. Okay? So if this is high resistance, you're going to get less current. If this is high resistance, you're going to get less current. It's going back to that idea of resistance. Excuse me. The important thing, though, about current in parallel circuits is that that total current that leaves that battery is equal to the sum of those currents where the circuit bifurcates. Okay, so when it hits this point, the circuit bifurcates the current. It bifurcates the current between these 2 points. And that shouldn't be all that hard to understand if you remember that current is charge per second. So the amount of charge, the rate in which charge is moving through the circuit, has to remain relatively constant over remains constant over the entire circuit. So that means that the amount of charge going through here, this small section here, has to equal the amount of charge going through this section here, and then through the thin sections again through here. So the amount of charge, the rate in which charge is moving, has to remain constant. So that should lead to you to this thought, this idea here. Let me make that equal sign a little bigger so you can see it, plus sign a little bigger so you can see it, that the total current that leaves that voltage is equal to the sum of the currents across this bifurcated section of the circuit, which we call parallel. Okay? Cool? From there, we can tackle this idea, we can figure out what the total resistance is. If I can figure out the total resistance, I can figure out what IT is, this total current. I mean, if you look back at series circuits, that's the first step of solving any sort of circuit problem, is to be able to determine the amount of current that's coming out of that voltage. Well, we need to use this to do it. We need to have this idea in place in order to do that. Now, what I'm going to do is I'm going to say, well, Ohm's law would say that the voltage total is equal to the current total times the resistance total. Okay? Or if I move the terms around, I'm going to get voltage total over resistance total is equal to current total. Cool? So substitute in, I get voltage total over resistance total is equal to, and then I have this I1 plus I2. Now, I want to put it in the same terms. I want to have voltages here. I want to have resistances here. So what I need to do is I need to apply Ohm's law to I1 and I2. And let's look at I1 and I2. So I1 and I2. I1 is the current going in this direction. I2 is the current going in this direction. But what's motivating that current? What's motivating the current to move? What's motivating the charge in that circuit to move in this direction? Voltage. Okay? So this voltage here is motivating charge to move. Now, if I want to talk about the current moving through this part of the circuit, I need to talk about the voltage through this part of the circuit. From A to B, what's my voltage from here to here? Well, remember that potential is always consumed. In a circuit, we're always consuming all that potential. This produces a potential, and as it goes through the course of the circuit, it's all consumed. So from A to B, with no resistors after B, how much voltage needs to be consumed from point A to point B? Now, I'm not asking you how much voltage this one's consumed or this one's consumed. Just how much is being consumed across A and B. The motivation for that current to move through that circuit is that voltage being consumed. Okay? Let's total. V total. That's the total voltage. There's no other way in which that voltage can be consumed. So all of the voltage here that's being produced has to be consumed across those two components. Okay? Same logic for 2. Okay? So, because I have voltage total all the way across, they go away. Then I'm left with this relationship here. And I'm going to write it relatively small, I guess. Well, I'll just erase this. So you're left with 1 over RT is equal to 1 over R1 plus 1 over R2 if I had more resistors, R3, R4, R5, R6. Okay? So that's our way in which we can calculate the total resistance in the circuit. Now, a lot of people make this mistake. They say, oh look, it's 1 over RT is equal to 1 over R1 plus 1 over R2. Flip the whole thing over and I get RT is equal to R1 plus R2. That's not how this works. Least common denominator. You can't do that until you can add up all these terms. To combine those R1s and R2s, so you can get one term over here, or one term, and then you can flip it. Okay, you can't flip it the way it is right now. Cool? Alright, so next thing I'm going to do is I'm going to do a simple problem talking about parallel circuits.